Good morning, everyone. I'm Shaopeng from Civil Engineering College of Civil Engineering at Hunan University. I am thrilled to be here at the 42nd ISARC to present our latest work. I would like to begin by extending my heartfelt thanks to my advisor, Professor Deng Lu, whose expertise and encouragement have been instrumental to this project. Today, I will be speaking about vision-guided camera pose estimation for robotic rebar tying. The slide outlines the structure of my presentation today, which will be divided into four main parts. First, I will begin with the research background and status. Let's begin by looking at the research background. The development of transportation infrastructure is a significant national priority, heavily supported by policies like China's 14th Five-Year Plan. This plan mandates that by 2035, prefabricated components must account for over 30% of the construction industry. This policy push is happening within a massive market. As you can see, the global reinforcing steel market was valued at over 224 billion US dollars in 2023 and is projected to grow to more than 317 billion by 2030. A key component in bridge construction, which is a major part of this infrastructure boom, is the box girder. Consequently, prefabricated girder factories are being established nationwide. However, production in these factories still relies heavily on manual labor. Therefore, our research focuses on a crucial bottleneck, the intelligent production of steel skeletons. As these images illustrate, the process of overtying is fundamental and widespread, essential in building, bridge, and tunnel construction. However, this crucial task is currently characterized by high workload, low levels of industrialization, and significant labor intensity. This creates a bottleneck in construction efficiency and a challenging environment for workers. Therefore, there is an urgent need to improve the level of industrialization and intelligence in the reporting process. Looking at the current research status, several companies in America, Japan, and China have developed intelligent reporting equipment. However, our investigation reveals a significant gap. Most existing robots are designed for tying rebars on flat horizontal surfaces, such as floor slabs. There is a distinct lack of mature robotic solutions for complex three-dimensional steel skeletons, like the vertical components found in many structures. This is the specific challenge our research aims to address. Now let's move on to the second part of my presentation, the main research contents. To begin, we first need to define what constitutes an optimal camera pose for our task. As illustrated in the diagram, we define the optimal pose as a position where the camera's x-axis is parallel to the transverse rebars and its y-axis is parallel to the longitudinal rebars. This specific orientation is crucial for two reasons, as shown in the slide. Based on this definition, we propose a closed-loop framework for camera pose estimation, which is illustrated in the flowchart. The framework consists of three main modules: image processing, camera pose estimation, and image evaluation. We will now look at each of these modulars in detail. Let's first look at the image preprocessing step. The raw RGB image captured by our camera contains a lot of background noise, which can interface with feature matching. To solve this, we leverage the depth image captured simultaneously. By aligning the RGB and depth images, we can reconstruct a 3D point cloud of the size. The top layer Rebar mesh will lie on the plane closest to the camera's optical center. We use the ransack algorithm to perform plane fitting on the point cloud and extract this closest plane. By back-projecting the points from this extracted plane, we can generate a clean, filtered top layer Rebar mesh image with the background effectively removed. This clean image is then used for key point localization. Now we move to the core of our framework, the camera pose estimation. This stage uses a powerful combination of superpoint and superglue. First, we take our filtered image from a random pose and a pre-captured reference image taken from the ideal pose. Both are fed into the super point network. Next, these detected key points and their descriptors are passed to superglue. It outputs a set of high-quality feature matches. With these matched 2D points and their corresponding 3D coordinates, we can then use the classic PNP algorithm to solve for the camera's 6 UF pose, that is, its rotation and translation relative to the ideal pose. After the PNP algorithm gives us an estimated pose, we enter the image evaluation loop. The robot moves the camera to this estimated pose, captures an image, and we apply the same filtering process. Then we calculate three quality metrics, dirty-U, dirty-V, and SUM-U. We have defined specific thresholds for these metrics from number of experiments. If the image meets these requirements, the pose is considered optimal and the process incomplete. If not, it means the camera hasn't reached the ideal pose yet. In that case, this image becomes the input for the next iteration of pose estimation, and the loop continues until the quality requirements are met. Let's proceed to the third section, where I will present our experiments and the corresponding results. To validate our method, we use the Rebar robot developed independent by our research group. Let's now discuss the experimental settings. We first establish the dataset to train the super-point network, which consists of 375 filtered images captured from the orange area shown in the image. The performance of our method was then tested on a different set of 375 images captured from the blue area. Now for the results. In our experiments, we recorded three key parameters for each initial pose scenario: whether the ideal pose was successfully reached, the number of attempts it took, and the computational time. The results are summarized in this table. The key takeaway is that across all 375 initial scenarios, our method achieves a 99.5% success rate within 3 attempts. Even more impressively, the success rate with just one single attempt was 91.5%. In terms of speed, the polar post method achieves an average computation time of just 1.05 seconds per estimation, making it highly suitable for practical applications. Having reviewed the results, I will now move to the final part of my talk, the conclusions and outlook. Our experiments showed this method is highly effective, achieving a 99.5% success rate within 3 attempts and a 91.5% success rate in a single attempt across 375 test cases. The average computation time of 1.05 seconds per estimation is fast enough for real-world scenarios. Looking forward, we recognize some limitations and opportunities for future work. The current method sometimes requires multiple adjustments and designed only for planar Rebar cages. Therefore, future research should focus on developing more efficient and robust post-estimation methods that can be applied to more complex structures, such as curved Rebar cages, along with corresponding image evaluation metrics. This concludes my presentation. Thank you for your time and attention. I will be happy to answer any questions you may have. Thank you very much.